Alright, let's make a start on integration. Before we do that, let's just look at what we've learned with differentiation. We know that if y equals ax to the power n plus c, then the gradient of y, dy of dx, equals, the power comes down, you take 1 away from the power, and any constant just becomes 0. So that's what we know so far. Agreed? Right. What I'd like you to do, let me pose you a question. Say I've got a couple of questions like this. And what these are the differential equations. In other words, this is what you get when you differentiate y. I'll give you 2 minutes. I'd like you to tell me what y could be. Okay, work in pairs, have a little think about it, and then we go for it. Off you go. Okay, so with part 1, you've got dy of dx equals x cubed. So let me write down part 1. What form can y take? Anyone? X to the power 4 plus c. Hands up if you agree.
No.
Go on.
Wouldn't it be 1 over 4x to the power 4 plus?
So you're saying let's add a quarter in there. Yeah? Hands up if you agree. Okay. And let's just see what happens when you differentiate it. We want to differentiate this, dy of dx. You bring the power down, take 1 away from the power, and that c just becomes a 0. So these 4's cancel. So you end up with x cubed. What about, let's just do the second one. What about if you've got dy of dx equals x to the 6? What form is my y going to take? Anyone? Somebody else? Go on.
X over 7 comparison.
Excellent. Is that okay? Should I add anything here?
Plus C.
Plus c. Alright, let's think about this plus c. The plus c is an arbitrary constant. Why do you need a plus c in there? This is why. Here's something I prepared earlier. Okay. Here I've plotted the first function where you've got x to the 4 divided by 4 plus some constant c. And this constant, I can move this around. See, I can move this around. Okay? And when we say it's a plus c, we're saying that c could be anything, it's going to cover all the cases. That arbitrary constant is a general solution. It's not a particular solution, it's a general one. A general means it covers all the possible scenarios that can possibly happen. It works for all of them. So in other words, if we were to take the gradient of fx, we get f prime x. So if I plot the gradient on every single point on fx, I'll get the red line here. Now look what happens when I change plus c. Does the gradient function change? In other words, the gradient function for all of these possibilities, no matter what c is, okay, as long as it's some sort of real number, is always going to be the same. It's going to be x cubed. And so that plus c factors in all of those possible variations that you can have. Does everyone understand that concept? Right? So that's our general solution. Alright, let's go back to our example. And let's now set out the whole platform or the whole sort of scenario for differentiation. What I'm going to do is draw a staircase. A 3-step staircase. On the first step, I'm going to write fx. Let's just make up some function x to the 4. Doesn't really matter. And on the next stair, I'm going to write down f prime x. So I've differentiated it with 4x cubed. And then we'll differentiate that again. And so forth. We can just carry on going down. Okay? So 4 times 3, 12, and you get x squared. This process is differentiation. Okay? The reverse process is called integration. You might want to copy this down. So integration is the reverse of differentiation. That means if you give me the gradient function f prime x and I integrate, I get fx. Okay. Now, the way we can lay this out, let me follow this with one or two examples. If I said dy over dx, or in fact, before we do that, let's just lay out the rules for integration. Let's say dy over dx equals ax to the power n plus b, then y equals the integral, and there's the integral sign, of ax to the power n plus b, and I'll write this out in a second, and this dx means with respect to x, I'll write that out in a second, and the formula for it is you raise the power by 1, divide it by the raised power, okay. Any constants become coefficients of x, and then you've got a constant of integration plus c in our general solution. So let me just fill in, let me just add a couple of notes. There's my integral sign, that means I'm integrating. Dx means with respect to x, because that's my variable, okay. Later on, as you'll see, you might have other variables like t or v, for example. And this part here is also quite important. This is called the constant of integration. And let's put that in a box. So this is quite an important line you need to copy down. And that tells you how to integrate. So if you give me the gradient, and you want to work out the original function, you can integrate the gradient by raising x to the power of 1, dividing by the raised power, and so on. Okay? With respect to. Okay, so with respect to. WRT. And so, if we've got, for example, dy over dx equals x cubed, we want to work out y, we'll integrate x cubed with respect to x. We raise the power by 1. I'm not even going to write down 4. I'm going to tell the examiner what I'm doing. I'm going to show with my method marks, and then plus some constant c. So this will give us x to the 4 divided by 4 plus some arbitrary constant c. Let's do another one. Say I've got, this time let's use different letters, ds over dt. ds over dt is 3t to the power of 4. We want to work out s. So we integrate 3t to the power of 4 with respect to t. This time we raise the power by 1. In fact, let me show the method marks. Let me show the method. So I'm going 4 plus 1 divided by the raised power. Okay, and then plus some constant c. And that gives us 3t to the power of 5 divided by 5 plus my constant c. Now this constant c, this arbitrary constant, okay, is 1 mark, normally 1 mark in an exam. Okay, 1 nice easy mark. Make sure you don't lose that. And that's for a general solution. The general solution, remember, covers all the possible cases we can get. One of the ways you might want to think about the bx part, so over here guys, we've got a question about bx plus c, where does that come from? Firstly, you always add a constant. Okay, you always add a c. Why? Because we just established from when we looked at the reverse process, we were adding a c. Yeah? When we're looking at the reverse process, we will add a c because we saw that the general solution, the plus c can be anything, it doesn't really matter. But pretend this was my equation, I'll get x cubed. Pretend this was my equation, I'll still get x cubed. Okay, so therefore you need that plus c in there because it's a general solution. Now the bx part, one way you can think about it is next to this b here, okay, you've got x to the naught. And so when you raise the power by 1, it becomes x to the 1 divided by 1. That's one way you can look at it. But basically when you're integrating a constant, it becomes the constant times x. Okay, because of the reverse process. Now look, if you were to differentiate bx, you'll end up with b. Okay, so that's essentially what it is. The integration is the reverse of differentiation, and we do it by raising the power by 1, dividing by the raised power, doing that for all the terms, and then adding a constant of integration. Is that clear? Is that okay? Alright, great. Let's have a look at some questions. I'll put a couple of these up and then we'll go over them. I'll give you about 5 minutes to do them. Can you have a go at these questions here? Okay. Okay, there you go. Alright, off you go. I'll give you about 3 minutes, 3 or 4 minutes to do. So, with the first one, what do we get? Y equals, what do you get?
x4
over 4 plus
3x squared over 2.
Excellent. Plus
2x.
Plus C. Excellent. Well done. Okay, the next one, Francesca.
I was doing these questions.
Okay. Andrew. Okay, hang on. 4 over 3 x cubed minus 5 over 2 minus x plus c. Excellent. The next one, Charlie. Okay. Alana.
Is that the third one?
Yeah.
I think that's that one.
Okay, who did? Hands up if you did. Okay, Jude.
X cubed over 3
Okay, let's expand this out. So you get x squared
plus x minus 6
plus x minus 6, and therefore y equals x cubed over 3.
plus 0.5x squared
Yeah.
minus 6x plus c.
Okay, excellent. Okay. Now, all of these solutions are general solutions. The reason why they're general is because we have the plus c. And that plus c means c can be any real number. Okay. But what if we don't want a general solution, we want a specific solution? Well, then we need to specify that in the actual question. And here's such a question. Let's look at example 3. Okay. So the gradient of a curve is given by dy of dx equals x squared plus 2x plus 1. Okay, the curve passes through this point 1, 5. Find the equation of the curve. First thing, with dy of dx, if we expand that out, we've got 2x cubed plus x squared. What can we do from here? How are we going to find the equation of the curve? Integrate. So if you integrate, let's write that out, 2x cubed plus x squared dx. Okay. Giovanna, what do you get for the first term?
You get 2x, well, a half x. Well,
Yeah, excellent. So yeah, so that's just 2 divided by 4, which is a half. Yeah. Okay. For the second term, Whitney, what would you get for x squared when you integrate it? Okay, Sumaya, do you want to jump in? Sorry, Shami, do you want to jump in? X squared when you integrate it.
X cubed.
Right. So you raise the power by 1, divide it by the raised power. Is that okay, Whitney? Okay, let me come back to that. So when we integrate, and you raise the power by 1, divide it by the raised power, and then what else do we need? What's missing?
C.
Plus C. Okay. Now they've given us some information. What have they told us about the curve? Kulsum. What have they told us about this curve? So when x equals 1, what does y equal to? Y equals 5. Therefore, we can substitute x, we can substitute y, and work out what c is. Can somebody work that out? In fact, can you all have a go at working it out? And then,
wait, are you allowed to practice in the sequence?
yeah, you can use a calculator if you want. Excellent. Okay, so c equals 25 over 6. All right. With partial fractions, the important thing to realize at the very outset is that the way to solve these isn't to go head on and start applying some algebra. Okay, as you see, if you do that, you'll end up some awkward sort of results which don't work. The essential thing about partial fractions is to recognize the pattern. Once you recognize the pattern or the case that we're dealing with, you will then have some understanding, some idea of what the answer is going to look like. And then you go about solving it. So we'll be covering 3 cases. Okay, I think in Edexcel they extend it and maybe do a variation of one of these cases. But we're basically doing 3 cases, and then we'll also come back and revisit some binomial expansion by mixing it in with partial fractions. Okay, so I'm going to sort of explain this using various cases. Case 1, let me copy this down, is when the fractions, you have fractions with linear factors in the denominator. Okay. And what we're saying is that if you've got an expression such as px plus q divided by ax plus b and cx plus d, okay, so you've got these linear factors in the denominator, then this can be written as ax plus b, cx plus d, and some constants at the top. Let's call them a plus b. You've done this? Okay. And so we've done, have we had a look at, let's have a look at, let's have a look. So with something like this, let's just recap then. Say I give you x minus 9 divided by x plus 1, 2x take away 3. How could you write that out? So this is an example we did yesterday. How would you write that out? Go on. Go on then. What do you get for x plus 1?
Yeah, a equals a over x plus 1.
Yeah. Yeah. And then what's a and b?
A equals 2.
Yeah. Minus 3. Okay, brilliant. Okay, so let's write minus 3 in there. Alright, and then as another example, what about when we've got something like this? 1 over x squared plus x take away 2. What do we do with this? Factorize it, good. When you factorize it, what do you get?
X plus 2 and x minus 1.
Excellent. And then we can write that as a over x minus 1 plus b over x plus 2.
No matter which way you round you
No, either way is fine. In fact, I don't need these brackets here. Okay, and therefore, what do you get for a when you solve that? Or, in fact, how do you set it up so you can solve it? Erisa.
You write a bracket x plus 2 plus b bracket x minus 1.
Yeah,
And then you find the number for x that will cancel out.
yeah.
b, for example, and be 1.
So b equals 1.
X equals 1.
Okay, so you've substituted what? What do you substitute x equals 1?
Yeah.
Okay, so what do you get for a?
And
A third, excellent. And then we substitute, what else do we substitute? X equals, how do you get rid of the a? What can we substitute? Derek, what do you substitute in here to get rid of the a? Curtis? 2. 2 plus 2 gives us 4. Minus 2. Okay, and therefore b gives us what? Anyone? Minus a third. Okay. Okay, case 2, let's write this down. Case 2 is when you have fractions with quadratic factors in the denominator. Okay. So, for example, if you've got something like, making this up, px squared plus qx plus r divided by ax squared plus bx plus c. So there's my quadratic. Let me just highlight that. That's what I mean by quadratic factor in the denominator. In fact, why not underline this? There you go. Okay. And let's multiply it by linear. Let's say it's dx plus e. Then something like this can be written in the form of ax squared plus bx plus c and dx plus e. So I've split them up. Now on top, because I've got a linear here, to make it a proper fraction and to cover all the possible scenarios, to go one down from a linear, I get a constant. Whereas here I've got a quadratic, and again to retain it as a proper fraction, which covers all the possible variations or scenarios that I might get, this therefore has to be a linear. So I'll call it ax plus b. Okay, and that's a general skeleton for looking at cases where you have a quadratic in your denominator.
say A times plus B.
AX plus B. AX plus B. It's a linear expression. Why? Because below it I've got quadratic, and so as a proper fraction, above it, I mean, it could be A is 0, for example. In some cases, I'll have it. But the point is, what if A isn't 0? But as a proper fraction, if I've got a quadratic below, then I'll obviously have a linear above. What if I've got a cubic below? What would be above it? Quadratic. Okay, so you get the idea. Yeah.
Could you then separate that? You know, you've got the quadratic, could you then factorize that?
If you can factorize it, yeah. But if you can't, then no, yeah. So it depends. But if you could factorize it, then I guess that quadratic would break up into some linears, isn't it? Yeah, 2 linears. And in that case, you wouldn't have this case 2, you'll have case 1. We've got linear factors below it, in which case you just separate them out and put a constant at the top. But in this case, you've got a quadratic which you can't factorize now, and hence we're doing it this way. Yes. The arrows, I'm just implying just a relationship between the numerator and the denominator, and saying it's 1 power less above than it is below. Okay, you don't obviously write them in there. Let's look at an example. Say I've got 2x plus 1 divided by x squared plus 1 times x minus 2. Okay. Here's say I'd write that as ax plus b divided by x squared plus 1 plus c over x minus 2. And then you just do the same process we did before, where you multiply both sides by the denominator over here. Okay, x squared plus 1 times x minus 2. So you multiply both sides by that, and then you solve to by substituting in values to get a, b, and c. So I'll give you a minute or two, have a go at that, and then we'll go over it. What we're going to do? What's the general process? Multiply both sides by what? Yeah, good, the denominator. So therefore on my left side we'll end up with 2x plus 1. On my right side we've got ax plus b times x minus 2. Make sure you use the bracket. Plus c times x squared plus 1. So there's our equation we now need to play with. If we substitute x equals 2 in here, this whole thing becomes 0. So we've got 1 equals 0 plus, maybe I should write 0 plus just so people can see that. You get 0, I've got ax plus b times 0 plus c times minus 2 squared is 4, plus 1 is 5. And so we've got, hang on, this part is wrong. Yeah, so that's 2. 2 times 2 is 4, so that gives you 5. So 5 equals 5c, and c therefore equals 1. Yeah? Sorry?
If x is 2, then it should be 2a plus b.
No, because I know that this part here is just going to give me 0. That's why I've chosen 2. We've chosen 2 because we've got x minus 2 here. And 2 taken away 2 is 0. So I know that's the reason why we've chosen 2. To make this part, this whole thing, this part here equal to 0. Is that okay? One second. Okay. Alright. So we've got the C part. Now we need to work on A and B. Okay. What can we substitute in to get rid of the A? What's the other most favourite value of x we normally substitute in? 0. So substitute x equals 0, and let's see what happens. You get 1 equals, so we've selected in 0 to get rid of the a, so you've got a b times minus 2, plus we know c is 1, so 1 times 0 plus 1. And so you've got 1 equals minus 2b plus 1. And therefore b equals 0. One take away 1 is 0, so b must be equal to 0. Is that okay? Now we're left with trying to work out b. What can we do from here? Ruben. Craig. So we substitute in 2 and 0. So that trick's worked so far.
You can use any.
Sorry?
You can use whatever you want for x because you know b and c.
That's right. They do work for all values of x. So this is true for all values of x. But we obviously take in things like x equals 2 or x equals 0 to eliminate certain numbers. But what can we do from here then? How do we work out b? How do you work out a? Sorry.
You use what x equals 1.
X equals 1, yeah. And we know what b is, and we know what c is. Yeah, you can do that. That's one way. Rabia, do you have another suggestion? Working out a. So we worked out b and c.
Compare the coefficients of x squared.
Why x squared?
Because it would be easy. You could compare the coefficients for x, but it would be easier because I can already see that the coefficient of x squared here is a,
Yeah.
and that the coefficient of there is coefficient over no. That's a bad idea.
Not yet. That's right. If you compare the coefficients, you can compare the coefficients of anything involving x. So you can do it of x even.
Or yeah.
Okay. And in fact, if you look at the coefficients of x, then on the left hand side you've got 2 or 2x. Let's just write the whole thing down. And on the right hand side
Minus 2a.
you've got where are we?
Minus 2a and 13.
Minus 2a. Is that right?
No, minus 2a, and then you've got 13. Is that 13? Or is it
No, that's b.
Oh, that's b.
That's b. Okay? And that's the only way we can get x, isn't it? That's the only way we can get x on the right hand side. And on the left hand side we've only got 1x. So therefore a must be what?
Minus 1.
A equals minus 1. Frank.
If you could get bx.
But he's already found b.
B, yeah, oh, b is 0. Yeah, so you can write 0x over here. We could do that, I guess. Yeah, so that's one way. Or we can compare the coefficients. If that doesn't work, you could do x squared. Let's see what we get. On the left hand side, there's 0x squared. On the right hand side, you've got ax times x, which gives us ax squared. And is there any other way? Oh, we've got the cx squared. Is that right? And c is 1. We know c equals 1. Therefore, a has to be minus 1 in order to get the 0. So you can compare coefficients. And that's obviously the different ways. Like Craig said, you can actually put some values for x, but it's probably easier just to compare the coefficients at this stage.
Yeah, I already did that.
The compare coefficients are a different method.
It's a different method to the one to where we substitute them in, yeah. Yeah, because why is it different? Well, when you're substituting here, like when you substitute 2, what's the idea, what's the thinking behind it? What substitute is, well, we want to work out c, we can get rid of all of this, make life easier. Well, that's quite easy. Just put x equals 2, and that's why we put 2 in. Okay? And then you think, well, let's work out something else. You think, well, I could put x equals 1 in, that would get rid of the c, but I'm still left with 2 terms, so it's not worth putting 1 in. But I could put x equals 0, and that's really common. 0 always gives you something, generally speaking, anyway. So if you put x equals 0, then that gets rid of the a. We know what c is, and then therefore we can work out b. So we've done our substitution part. So you think, well, what's next? What can we substitute in next to work out what a is going to be? And there isn't something evident, like minus 1 or 0. Okay? So in this case, it's good to then start comparing coefficients. And say, well, if you expand this out, the right-hand side has to be equal to the left-hand side. And so why don't you just look at x squared terms? Because obviously I'm going to get an x squared term here. Or you can just look at x terms, okay, depending on what you've got. Okay. So it's still part of the process. I wouldn't start comparing coefficients from the outset. I'll probably do substitutions and then go on to comparing coefficients. Alright, is that okay so far? Right, so far what we've had is fractions where you've got linear factors in the denominator. Okay. And fractions where you've got a quadratic factor in your denominator. Okay. What I'd like you to do, I'm going to pose this question and I want you to come up with a suggestion about how you can write this out as a fraction and then try and solve it. So case 3 is similar to case 1, I guess, is fractions with repeated linear factors in the denominator. So it's repeated. So in other words, if you've got something like px plus q divided by ax plus b times ax plus b, how would you write this out? Have a little discussion, and then how would you then solve it? And are there any potential problems that you might encounter? I'll give you a minute to have a little think about that, and then I'll give you the general expression of solving something like that. Alright guys, so what do we have? How can we write this? How can we write this out? So you've got a linear at the bottom. If we were to write this out as ax plus b, and then put some numbers in, say let's put a and b. What's the problem with that? Is there a problem? A and b, will they be the same? So if we because they're linear factors at the bottom, if we then apply case 1, okay, because this is a repeated linear, okay, so you've got two linears. If we apply case 1, what's going to happen?
They'll both cancel out when you cancel one.
Say that again?
They'll both cancel out when you try to cancel one.
Right. Okay. Jack, do you want to say? Okay, somebody else? Okay. So, because the denominators are the same, we can write this out as ax plus b, a plus b. Okay. And that doesn't really give us anything, because then we're left with a px plus q divided by ax plus b squared equals a plus b over ax plus b. It doesn't really work. Yeah, you've got a quadratic at the bottom, a linear at the top, and then on the right hand side you're left with some coefficients and some numbers. But if you don't believe me, the best thing to do is actually, when I give you one of these questions, try and do it this way and see what you get and see if you can actually do it. So let's look at something like this. Oh, before we actually look at something, the way to do it is to do the following. So let's get rid of this. The way to do it is actually to, because you've got a repeated root here, what we'll do is a little trick and we'll put a square in. Okay, so there's our little trick, is to put a square in. Okay, so that's case 3. When you've got a repeated linear factor, you then put a square in, and that is something we can do to give us a good solution to a problem like this. So 4x plus 4. If we factorize the bottom, what do we get? Somebody factorize the bottom? X minus 2 squared. Now it's a repeated linear factor. Therefore we'll write x minus 2 squared. And we'll put two integers at the top, a and b. Notice I haven't put a linear at the top of x minus 2 squared. I've just put an integer. Okay, and that's deliberate so that when we actually multiply it out, So if I was to multiply this top and bottom, top both sides by x minus 2 squared, okay, then we end up with 3x minus 1 equals a x minus 2 plus b. Now here, what can we substitute in for x to get rid of the a? Who was asking me? Tadas. What can I substitute for x to get rid of the a? 2. Excellent. So substitute 2. So that gives us 6 take away 1 equals 0 plus b. And therefore b equals 5. If b equals 5, what does a equal to? So we can put in any value, I guess. Or you could compare coefficients. You can compare the coefficients of x. So on the left hand side we've got 3x. On the right hand side we've got ax. And therefore a has to be equal to 3. And so therefore we should now tell the examiner our final answer. 3x over 1 x minus 2 all squared equals to 3, just give me a second, 3x minus 2 plus b 5 over x minus 2 all squared. Yeah.
I know there's a bit that behind for that.
That's fine.
You know, b over x minus 2 squared or x squared.
Alright, so that's a little trick we've done. Alright, so you've got a repeated linear.
Yeah.
If we apply case 1 and write that linear twice,
Yeah.
so you write ax plus b, ax plus b,
Yeah.
if you then try and solve that,
Yeah.
it doesn't work. What I'll suggest you do, in fact we can do this here, let me use a different colour, okay? Let's do it. 3x minus 1, x minus 2, x minus 2. So you've got two linears, right? I told you in case 1 you can write that as a over x minus 1 plus b over x minus 1. Yeah, two linears, correct? If you then multiply that out, we end up with 3x minus 1 equals, sorry, why have I written 2? So that's x minus 2. So that gives me a x minus 2 plus b x minus 2. Correct? If we solve that, we've got a plus b x minus 2. So you've got ax plus b equals 3x. I guess you'll have to set up some sort of equation. Let's write 3x minus 1. How do you solve that? Anyone? How do you solve this? How do you find a and b in this? So you know that 3x equals ax plus bx. You've got that equation. And then you've got minus 1 equals minus 2a minus 2b, isn't it? Yeah. If you then multiply the top number by, so there's my equation 1, there's equation 2. So I've set up some sort of simultaneous equations. If we were to multiply the top one by minus 2, say, so you get minus 6x equals minus 2a minus 2b x, still left with a problem. Doesn't work. Yeah.
When you did that, if you cancel out one of the x minus 2 times,
Say that again?
do you leave it as a x minus 2 squared and being x minus 2, or can you cancel one out? And get
From
rid of
here, this has our final answer here.
it?
Yeah, no, you leave it as squared. You leave that square in there. So that's the little trick. So Craig, over here we didn't have that square in. See here, there isn't a square there.
Yeah.
It's just two linears.
Yeah.
But because they're repeated, you end up with this sort of problem. Okay. So in order to overcome that problem, we'll say, well, the skeleton of the answer has to look like this. There has to be because it's repeated. If it wasn't repeated, then it'll be case 1, 2 linears at the bottom, which you can then write out. That's not a problem. But obviously, when it's repeated, you end up with this scenario here where it doesn't work.
Yeah.
Yeah, because A essentially is B. Yeah, A plus B over. I mean, you could just, this part can just be written as A plus B over X minus 2. And the reason why it doesn't work is because your equations don't match up. You've got this going on. Yeah, you've got a linear over a quadratic equals some number over a linear. Because they don't quite balance out. Go on, Robbie.
Could you just multiply the top and the bottom by x minus 2 for a and b?
By X minus 2.
Yeah, so you've got a plus b into x minus 2 and then, yeah,
Okay, so you've got X minus 2.
and then divided by x minus 2 whole square.
So that just carries on. 3x minus 1 divided by x minus 2. What would you do from here? You're still left with this scenario.
Wait.
What I'd suggest, have a play around with it. If you come up with something interesting, go on.
So wouldn't the bottom be x minus 2 whole square though?
No, because you just times both sides by x minus 2.
That's true, so I could have some out.
Okay? But in order to avoid this problem, you do a repeated root. Yeah? Scenario.